All right. Good morning, everyone. Can you guys hear me?
Yep.
All right. Hope your Easter went well. Whatever you celebrate, got a little rest after the exam. We haven't started grading them yet. Probably try to get them back to you by the end of the week, but we wanted to go through the key carefully and make sure we had the right rubric and everything before we get started. So probably Friday. Today, we're going to finish chapter 7, and the readings are a little bit ahead. So part of the reading assignment is chapter 8, but we really won't get to that until Wednesday. What I want to talk about today, or continue talking about, are the stereochemical outcomes of different reactions. And this is it's an important topic because, most organic molecules are going to have stereocenters. I shouldn't say most. There's plenty that are just like flat. A lot of drugs are just like flat polyaromatics, without any chirality. But most interesting molecules, I'll say, have stereocenters. And if we're thinking about making them, we need to think about controlling the stereochemistry at one position or two or three or however many stereocenters there are. And in order to think about controlling stereochemistry, I have to know, what the stereochemical outcome of various reactions, what I can anticipate. And, what makes organic chemistry interesting, and synthesis in particular interesting, is that, we learn all these kind of guidelines and models, but when you get to sort of complex molecules, a lot of this stuff breaks down very quickly. And I think, for the research that we do, the molecules that I get most excited about, the ones that students get excited about, are ones that, we just don't know. We don't know what the stereochemical outcome of a given transformation will be for, a whole laundry list of reasons. But anyway, that being said, there are basic principles that we can use to sort of get us started, even if they're, not totally sufficient in all cases. To a first approximation, the way you think about how to set a stereocenter, how to control stereochemistry, is to think about mechanism. And if you have an understanding of mechanism, you can predict, what you think the substrate might do. And hopefully we can sort of culminate today's lecture. Hopefully will culminate in a real world example of this if we have time. So the reason why we're going through all this is so that you understand that stereochemistry derives from mechanism. Understanding mechanism allows you, to predict stereochemistry. Often those predictions, are thwarted for various interesting reasons, but we want to be able to say something. So anyway, we're going to continue with some examples. I'm going to have hydroboration in there, which was, as the stereochemistry of hydroboration effectively was a bonus problem on the exam. If you were able to get that, great. If not, basically going to give you the solution here. And we'll talk about a couple other reactions. So just by way of reminder, because I know everyone probably had their mind on the exam last week, we talked about reactions that proceed by what we call anti-addition. So So when we say anti-addition, we mean that the groups that added to the alkene end up on opposite faces of the alkene. And the two examples that we were playing with were cis and trans 2-butene. So this is trans or E2-butene. We can add bromine to that. And the bromonium ion can form okay. And then I can open this by backside displacement with bromide. So we said in this mechanism, you make the bromonium ion, and then that bromonium ion opens up via a specific, or through a specific trajectory, and that is backside displacement. And when we get to nucleophilic substitution very quickly here, we'll give you like a MO explanation for this. But for now, you'll take my word when I say that it comes in the back. And what we form is this compound. Okay. And we were doing a lot of comparing compounds and, rotations and gymnastics with them, but we can also remember rotate bonds. And so if I rotate about that central carbon-carbon bond by 180 degrees, I get to this structure here. And this structure, of course, is meso or achiral, okay? And what you should convince yourself of is that attack at the other carbon, so gives the same product, okay? As does formation of the enantiomeric bromonium ion intermediate. So attack of the bromine from the bottom face. So okay, so you add on the bottom, you get the enantiomer, and if you open that up, you actually get the identical product, okay? And so I convince yourself of this on your own, work through those other possibilities. It's just good exercise. The other thing is that I'm not going to try and generalize from this outcome just because the symmetry of this system and the symmetry of what you're adding two of the same substituents, sort of is what leads to this meso structure. You could probably make some generalizations, but they're just not that. You're just not going to see this that frequently. It's better just to work through the mechanism and then, assess what the possibilities are in that through that approach, rather than trying to make generalizations, which I said I don't think will be very general. All right, so the other example that we covered was Cis2 Butane. Just draw that really quickly here. And so cis or Z2 butene. And if you add bromine to this, very simple, form the bromonium ion. And this ion, so bromonium ion that you form on the top gets formed as a mixture of enantiomers. This one on the bottom is meso. And so let me just emphasize that. So this is plus minus, this is meso, okay? And you can open this at either side. So and just call these A and B. And if you open at A, you get this structure. And then if one opens up at B, get to that structure. Okay. And these two compounds, hopefully you can see it, are enantiomers. The way it worked out, if I just draw a mirror plane and then start reflecting, I don't actually have to do anything to the molecule, and you can just start seeing that one is hopefully you can see that one is exactly the enantiomer of the other. So okay, so the point is that depending on the alkene geometry, the same reaction gives a different stereochemical outcome. And again, don't try and memorize trans goes to meso. You know, I mean, again, that there's some generality to that, but you're better off, trust me, you're better off just working through the mechanism. But the alkene geometry matters, and the way that we think about it mattering, or the way we understand it, is through the mechanism. So you make the bromonium ion, and then that has to open by backside attack. Okay, you don't have bromine coming in from the same side as the Br plus in the bromonium ion. That would give you a different stereochemical outcome. Okay, so to get to the right answer, you really need to know, you know, how these reactions are going to proceed. And so there is one generalization that you need to know, and I've already said it. I'll say it again here. Combination of achiral starting materials and reagents, so no stereocenters in anything that's reacting, always leads to racemic product or achiral meso product. Okay, so I can never go from, essentially another way to put this is I can never go from no chirality in a sample or no enrichment in chirality to enrichment. It's not physically possible. Okay, so if you're getting to solutions, if you've got achiral and achiral and you're running reactions and you're only finding like one enantiomer, you're missing something. There's going to be the other enantiomer, or the compound should be meso or something like that, but you shouldn't be able to spontaneously generate chirality. Okay. All right, so that was this is the addition. We've gone through the addition of Br2 in cyclic and acyclic systems, okay? And it's tricky because, you know, you have to make sure that you're drawing, you know, everything accurately and sort of, you know, changing chemistry as needed in the right way. Fortunately, acyclic or cyclic systems are actually a lot easier to see, I think. And so I just want to cover an example of that so you've seen it. And so let's start with like cyclohexene, for example. Okay. So if I brominate, if I add Br2 to this substrate, the product that I form is always what we call the trans dibermide. So,
Sorry, Professor Herzon, is that meant to be a square or a hexagon?
Sorry, this is a hexagon. Yeah. 6-membered ring. The cyclohexene. So I make the trans dibermide. So this is, okay, the product that I get out. And that product is chiral, okay? You can draw a non-superimposable mirror image for it. And so if I'm making a chiral product and everything I start with is achiral, this must be racemic, so I can draw plus minus, okay? So it's formed as a 1-to-1 mixture of enantiomers. The product that there's another product, if we count each enantiomer as one product, there's a third product, which I don't observe, which is the Cis Dibermide. And so this compound, of course, is meso. It has a plane of symmetry right down the middle. So I don't need to worry about enantiomers, but it is a diastereomer of the trans dibermide. It is a stereoisomer that is not a mirror image, right? And so this diastereomer does not form. The reason it does not form is because of the mechanism. So if we now draw it for this substrate, we can draw our bromonium ion. So I'm kind of looking at the rings sort of in a perpendicular orientation. Okay, there's my bromonium ion intermediate. Okay, and hopefully this perspective helps you to see that this requirement for backside attack means that I'm coming in from the bottom face if my Br plus is sitting on the top face as I've drawn it. Okay. And what that leads to then is this type of stereochemical arrangement. So I have Br up here, H down, and then H up, Br down, okay? So if I want to track, you know, if I could like hypothetically label the bromines, it would be A and B, okay? And then as bromine B comes in on the bottom, as it's doing that backside attack, this hydrogen gets pushed up, right? So this guy is going to slide up through the ring. And if we wanted to label it, it's right there. So it's what we call an inversion of configuration. You're kind of changing the configuration in this step. But the point is that you get the trans dibermide, and this is the same compound as what I drew on the top. Again, you should convince yourself, please take the time to do this, that if I get to the alternate bromonium ion intermediate, where I add bromine to the bottom face of the alkene, I'm going to form the enantiomer of what I've drawn, and that's how you get the racemic mixture. So okay, so it leads to, you get the enantiomeric bromonium ion, and that leads to the enantiomer of the product that I've drawn, okay? And so we generalize this process by, or we can sort of talk about this by using the term anti-addition. We say that the addition of bromine to an olefin proceeds in an anti-fashion. The elements of bromine get added to the opposite sides of the alkene, okay? And, you know, arguably it'd be better to introduce this by starting with the cyclic alkene. You can see very clearly that the bromines are on opposite sides of the ring. It's an anti-addition. Still an anti-addition in the acyclic alkenes, but it's just a little trickier to see because you have free bond rotation and you have to manually kind of like, you know, invert things as you're drawing. So that's a little trickier, but it's still correctly characterized as an anti-addition, okay? And as you might expect, there are a lot of reactions then that proceed by what we call Syn Addition, all right? And so in a Syn addition, the reagents are going to add to the same side of the alkene. And let me go to a new board here. In a Syn addition, the reagents end up on the same side of the alkene. Good example of this, I think I mentioned this. Did we cover hydrogenation in class? Does anyone remember?
Yeah, we did. This is the case when you have like H2 adding, correct?
Yeah, exactly. H2 adding across an alkene. I know I probably just mentioned it and stayed away from mechanism because there's lots of different catalysts that you can use for that, and they all have different mechanisms. But a commonality, when you do have a mechanistic commonality, is that you get Syn addition of H2 to an alkene. So let's say we have dimethyl cyclohexene, okay? If I treat this with some sort of catalyst, typically going to be platinum or palladium and dihydrogen gas, I can add H2 to the alkene, and that addition always occurs in a Syn fashion. The H2 ends up on the same side of the alkene. So I gotta say, one of the things I don't miss about in-person lectures is ending up as like a ball of chalk at the end of class. I used to get chalk like head to toe. It's a complete mess. my clothes are a mess. Like, it doesn't come out until you wash your clothes. It's like, it was definitely a hazard of the job, you know. That and paper cuts are the most dangerous things I have to deal with. All right, so anyway, so H2 adds to the same side. This is the product that you get if we add to the top face, okay? This product is meso, oh Jesus. This product is meso, and it has a plane of symmetry down the middle. Please convince yourself on your own that addition to the bottom face gives you the same product. You just flip it over, okay? So H2 adds the same side of the alkene, Syn Addition, all right? And so why is that the case? It comes from mechanism, all right? And so, you know, one of the things about us chemists is that we're reductionists. We like to be able to describe things at sort of the atomistic level. Here, I'm going to give you a little cartoon, and it's the best I can do. So you'll forgive me. But the way we describe hydrogenation as occurring mechanistically is that you've got your platinum or palladium catalyst, which is typically going to be what we call heterogeneous. It doesn't dissolve in solution. It's just like a black powder that you add. And when that sees dihydrogen, we say that the hydrogen gets absorbed on the surface of the catalyst. So this box is meant to denote catalyst surfaced. And this is, you know, a metal, a mixture of metals. And then the alkene's going to come along and associate with this. And so let me just, so I do the same, I'm just going to put these on the bottom here so everything maintains the same orientation. So the H2 adds across the catalyst. We say that you get these like metal hydrides, and then your alkene comes along, and that's where it adds in a cis fashion. So if I draw the alkene sort of with perspective, what we say is that the H's come in on the same side of the alkene. Okay, so kind of like just adds it, and then that gives you this stereochemical outcome. So you always get the cis diastereomer in the product. The methyl groups are always on the same side in the product, okay? And, you know, that's a feature of, that is directly determined by the mechanism, but these types of, you know, reliable stereochemical outcomes are very valuable to us, you know, because it allows me to think about, you know, if I'm confronted with a molecule where I've got, you know, two methyl groups on the same side of the ring and they're adjacent to one another, I know that that can come potentially from reduction of an alkene, right? I just hydrogenate it. And the alkene itself gets me to a whole bunch of different chemistry. So as I'm thinking about putting this molecule together, you know, actually, you know, making this type of structure de novo is challenging because there's no functional groups. There's nothing to really work with. But making the corresponding alkene, I mean, I could probably buy it, but if I wanted to make it, be much easier, okay? And so the point is that, you know, any reaction that proceeds with high stereoselectivity, if it, you know, if it always gives you anti or it always gives you cis, you know, whatever the outcome is, these are kind of tactics that we file away because they can help us, you know, when we see these types of substructures in more complex molecules. So anyway, so you also get Syn addition in an acyclic system. You just can't see it. And let me explain why. So like, for example, if I could hydrogenate this and then, you know, treat it with some sort of like H2 that I could keep track of, what I'd find is that I got okay. I got that product there. The H2 comes in on the same side of the alkene. And this product, of course, is not chiral because I have the other hydrogens at carbon. If I reduce this in the presence of deuterium gas, so I can't actually distinguish that chemically from the hydrogen that's already present, you would get something like this. Okay, and so those types of systems you'd be able to distinguish.
Could you do an example with like if you had kind of like the trans butene, but instead of H's you had like Cl's, if that made sense?
If you added like Cl2 across it?
So like let's say you had kind of that same molecule except it was trans.
Oh, you're saying Cl on the alkene.
Yeah, correct. Just to like be able to see it better.
Yeah, we can go through that, sure. So I think what you're asking for is is that what you want?
Yeah, and then do the hydrogenation of that.
Yeah, yeah. So you know, first looking at this, the only thing I can tell you is that, you know, you get Syn addition of hydride. I have to actually go through it to tell you if it's meso or if it's a mixture of enantiomers. So you're always, you know, point is you're always sort of working through these types of mechanisms. So yeah, so we can just add H2 in this one. And again, it's going to come from the top or the bottom, okay? Equal probability for either face. So we can consider both examples. So if you allow me, you know, given that we're using this cartoon mechanism, if you allow me just to draw the products, if anyone wants to go through the mechanism, we can just give me a shout out, but otherwise I'm just going to draw the products. So let's say that H2 comes in from the top face, okay? You could imagine coming in from the top face. So then I'm going to push the substituents on the alkene down, okay? And so I'm going to push that methyl group in the bottom left here down. It's coming out at me in this starting material, so it's still coming out at me. So it gets the wedge. And the chlorine gets the hash, okay? And then same thing on the other side, except the substituents are reversed. The chlorine's coming out at me in the starting material. It sort of maintains that region of space. It keeps the wedge in the product. And then the methyl group's going back, stays in that regime, gets the hash, and it's pointing down. And then, sorry, I messed this up. This is Cl back here. And then if you look at this molecule, you need to figure out if it's meso or DL or mixture of enantiomers, right? And I think it's chiral. I don't think this is the meso one, because I think if you rotate, yeah, for sure, this one is yeah, this one is chiral. It does not have a planar point of symmetry, okay? So we could go in from the other face, call this B. So this is like A product. And then the B product would be H from the bottom. So and then, so if you imagine sort of HB coming in on the bottom, I'm going to push this methyl group in the front up. It's going to remain in front, so it's a wedge. And my chlorine is up and back. And then on the right-hand side, my chlorine is up and out, and then my methyl group is up and back, right? And yeah, if you do an out-of-plane rotation of 180 degrees on one of these molecules, you can see that they're mirror images. So this is the B product. And so these are the enantiomers. And so like the correct answer to this question would have one of these structures and a plus minus, or if you want, you can draw both structures and a plus minus, or you can write equal amounts, whatever you want to write. But the point is you have to specifically indicate that you're getting two enantiomers of product is important, okay? All right, so hopefully that's helpful. So let me keep going then. So you know, again, just trying to point out certain reactions occur by anti-addition to an alkene, certain reactions occur by syn. We just did hydrogenation. That's always very reliably syn. The other one, which is very reliably syn, which is arguably a more powerful transformation, is hydroboration oxidation. So and H.C. Brown at Purdue was the guy that spent his career. He was like the boron guy. And when he started, he was like figuring out, you know, the basic chemistry of boron. You know, he must have started in the 50s and he's passed away now, but he was the one that really developed hydroboration oxidation and the chemistry of CB bond in general as into sort of, you know, very useful area of synthesis. So anyway, hydroboration oxidation is always Syn addition of H and OH, okay? And I put it in quotations because this is what we refer to as a indirect reaction. Hydroboration oxidation doesn't involve the direct addition of water to an alkene, but the net product, after you go through the hydroboration and then the oxidation and hydrolysis, the net product is what we call the formal addition of water to the alkene. I've added H and OH across the alkene in an indirect way, and so we call that a formal hydration or formal addition of water. But those two substituents in that final product are always on the same side of the alkene. It's always Syn addition, okay? And so as an example, so treat with borane, and then let me modify this just a little bit here. This is going to be H, so one methyl group on the ring. It allows me to make another point. So we always get Syn addition of the OH and the H in the very final product of this sequence, okay? And we also know that there's another element, which is where does the boron attach? Boron always goes to the less hindered carbon of the alkene, so my OH is going to wind up at the carbon that I asterisked there. And so the product that I always get is this. So okay, plus minus, okay? And so this is I'll put these in quotes maybe so you can make the connection. That's the H and the OH that come in the reaction, and they are on the same side of the alkene, okay? And so there's actually a whole slew of potential products here, and this is why, you know, we love this type of reaction, because you could imagine boron attaches to carbon, which would place the alcohol in the more hindered carbon. You could imagine the other diastereomer of that, so the anti, and then of course the diastereomer of this one. And this reaction is very reliable. Boron always goes to the less hindered carbon, and you always get this Syn addition. So anytime you can sort of have something that takes, you know, multiple sort of outcomes and cleanly directs it in one direction, that's a very useful reaction. So so we always get this, we never get the anti-addition product. So for example, so here, the elements that are added are on opposite sides of the ring. Okay, so that one is not formed. It's not generated. And why not? The answer, again, goes back to mechanism. So in the first step of this reaction, the borane associates with the alkene. And it's going to look something like this. So I'm going to use this side perspective again. Okay, so this goes on. The boron comes in, you add to the alkene, and the new CB bond and the new CH bond end up on the same side of the ring, okay? And then that boron gets further oxidized to a CO bond, but it is this first step that goes through this single four-center transition state that determines the stereochemistry of the reaction, okay? And again, it's a consequence of mechanism, you know, so I have boron and hydride coming in from the same side. It doesn't add in two steps. It doesn't add, you know, it's not like some weird termolecular mechanism. It's a bimolecular process. Syn addition proceeds through a single step, no intermediates. And so that is what leads to this reliable sense of addition, okay? And so this mechanism dictates the relative stereochemistry. So OH and H on the same side of the ring, okay? It doesn't control absolute stereochemistry. So again, please work through this on your own. If you work through the alternate transition state where you bring borane into the bottom of the alkene, the bottom as I've drawn it, you should arrive at the enantiomeric product, the product that is the enantiomer of what I've drawn here, okay? And so attack at either face is equally likely. And so you end up with racemic product, okay? And again, that you could just go back and say, okay, achiral starting material, achiral reagent, I must get a racemate or meso out of this, okay? So I just want to end, no, shoot. All right, we may not get through everything, but let me, I want to start something that will finish in the next lecture because it's important. So, okay, so let me just sort of take a few steps back here. So addition to the other face of this alkene leads to the enantiomer drawn. Enantiomer of what is drawn. Okay. And that enantiomer or that transition state is enantiomeric to the transition state that I've drawn. So okay. And so let me put that on, again, I'm moving a little bit faster here for time, but we went through this idea of enantiomeric transition states, I think in lecture 22 or 23. And so if that's at all, unclear, please go back and just review that. You'll have hopefully a clear explanation of it in those back lectures. But if I want to put that on an energy diagram, I can do it like this. So I've got my alkene plus BH3 that has some energy, and that's going to go via a single 4-center transition state. Sorry, let me make this one H. This should be H. Okay, so that's the transition state leading to one of the alkyl borane intermediates, and then this would be the enantiomer of that would be this one. Okay, and so if you do, and if you rotate this thing 180 degrees, hopefully you can see that it's those two transition states are enantiomeric. And so the point that I tried to drive home in the last lecture was that just like enantiomers having equal energies as ground state molecules, same applies to transition states. And so whatever the energy of this transition state is, I don't know what it is relative to starting material, but the two are identical, okay? So,
Professor?
yeah.
For the rightmost molecule, should the boron be attaching at the least substituted carbon? So it would actually be.
Yeah, thank you. Yeah. Yes, those two were not, in fact, enantiomers. Now they are enantiomers. Thank you. So you get, it's an enantiomeric transition state. The energy has to be identical. Okay. That is a fundamental property of enantiomers. And so we say that these delta G's are identical. Again, this hopefully is review. If it's not, please go back. These delta G double daggers are identical. You proceed to the two enantiomers of alkyl borane in this case with equal rates, okay? And so the thing that I want to put out there, and then we'll finish this in the next lecture, is what if those energies are not equal, okay? And for them not to be equal, they can't be, can't have that enantiomeric relationship anymore. And so what I want to put out there is this idea of diastereomeric transition states, okay? And so again, this is a little bit above what you need to know, but it's got to do some of the interesting stuff here, So if you take this molecule, this methyl cyclohexene derivative, so I just stuck a methyl on the ring, we're going to say that this is a single enantiomer, okay? Normally, if I just draw one enantiomer and don't show a plus minus sign, that implies to me that's a single enantiomer. I'm explicitly drawing single enantiomer here just so to distinguish it very clearly from a racemate, okay? So I've got a single enantiomer of that starting material, okay? If I do my hydroboration oxidation, okay, what is the stereochemical outcome? All right. And it's complicated. There's a lot that can happen here. So let's just talk through it from the very beginning. Okay. So where does boron attach? Well, I know boron attaches to the less hindered position of the carbon. So we're going to say B to C1, right? And then we know that the hydride goes to C2, right? Okay. And we know that we're going to get Syn addition of boron and hydrogen. And so Syn addition of H and OH. Okay. And so let's just say, like, I don't know, you know, I just want to think about this very slowly. So what I'm going to do is I'm going to draw the products of Syn addition, and then we'll discuss. So let's say we add to the top face of the alkene. I would get to that. So just one more minute and then I'll let you guys go. Okay. But then there's another product where it can add to the bottom. Okay. Okay. Can anyone quickly tell me what the relationship between these two compounds is?
They're diastereomers.
Yeah, why are they diastereomers?
Because they are not mirror images of each other.
Exactly. They're stereoisomers that are not superimposable mirror, or not non-superimposable mirror images of one another. They're diastereomers. Okay. And so what does that mean? That means they, in principle, have different energies, right? And what does that mean in terms of reaction mechanism? That means that the transition states leading to each of these products are diastereomeric. They're related by being diastereomers. And so what does that mean? Right? You see where this is going? That means that they can have different energies. And so what does that mean? That means that the delta G double daggers are different. Right, you can get selectivity for one or the other. The rates are going to be different. So these are not, in fact, formed as a one-to-one mixture. And that is very powerful. That is very powerful, because if you look what's happening in this reaction, I'm setting, we call it setting, I'm creating two more stereocenters in this transformation, right? That's always good. You know, it's very challenging to control stereochemistry. If I can reliably form one of these over the other, that could potentially be very useful to me. And the answer is, you know, I don't know if I could. You'd have to look at the energies, but in principle, you can. In principle, the rates of formation of these two products are going to be different. So I'll stop there, and we're going to drill down on this a little bit more. It'll be the last lecture on this sort of mechanism and stereochemistry, but we'll drill down on this example just a little bit more, and then I'll show you this molecule monensin that was made in the 70s. Beautiful example of using diastereo control, so existing stereocenters to control facial selectivity in the addition of borane to an alkene. And so, yeah, so maybe for your own homework, you know, we're rebooting here after the exam, you know, spend some time thinking about this reaction. Think about the two products and the transition states that precede them. And please think about the stereochemical relationship between those transition states. You should see that they're diastereomers of each other. And then we'll go through it in detail in the next lecture. You can sort of check your work, okay? All right, so again, like I said before, I think the issue with the videos is the pausing and stuff. So I'm going to stop. I'm going to let the video process, and then I'll come back for office hours. So probably, you in about 5 or 10 minutes. I'll sign back on. All right. All right. Thanks, everyone. I'll see you on Wednesday. Yeah.
Would it be possible just to go back to the other slide quickly? I just wanted to take a picture of it quickly.
Yeah. Which one did you want? The preceding one?
Yeah, the one before this with the energy states. Yeah. Thank you.
Yeah.
Okay. Thank you so much.
All right. Bye, everyone.